Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your ZyBooks Section 8.1 titled Sequences. So let's begin. Alright, so they got a survey here. Nah, I'm not doing that. Alright, so definition. A sequence is a special type of function in which the domain is a set of consecutive integers. For example, a sequence can be defined to denote a student's GPA for each of the 4 years the student attended college. The domain of this function would be 1, 2, 3, and 4, right? All the input, the first year, second year, third year, fourth year. And the function g is specified by the numerical values of the GPA in that year. So here's a sequence of four values, 4 terms. When a function is specified as a sequence, using subscripts to denote the input to the function is more common. So instead of g of 1, g of 2, g of 3 like usual function notation, you'll have g with a subscript to indicate what the input is. This is g sub k is the same thing as g of k, right? Instead of g of k. A value g sub k is called a term of a sequence, and k is the index of g sub k, right? So the subscript, the index variable. So the sequence up top here, instead of g of 1 equals, g of 2 equals, it's g sub g1 is 3.67, g2, g3, g4, first term, second term, third term, fourth term of this 4-term sequence. When the function name as in g and the indices are understood or not important, the sequence can be specified by just listing the terms. Put the GPA for the first year, second year, third year, fourth year, again, as long as it's understood what the sequence is representing. The entire sequence is denoted by some braces around g sub k, whereas gk, without any curly braces, is used to denote a single term, right? Just the kth term. So if you want to, again, describe or discuss the entire sequence, you put braces around the name of it. But if you want to discuss a single term, the kth term, you just look at it without the braces, g sub k. All right. While the first index is commonly 0 or 1, a sequence may start with any integer, as in the following example, right? So like the first term here has an input of -2, and we could call this the -2th term if you wanted to, I guess. Or just the first term, right? Because it's the first one you're seeing. And then it goes by ones, then plug in -1. Again, a series of consecutive integers, right? A set of consecutive integers makes up your domain for these functions. Right. A sequence with a finite domain is called a finite sequence, right? So this one they gave us an example of up here is a finite sequence. There is an initial index m and a final index n, right, where n is greater than or equal to m. The a sub m is the initial term, a sub n is the final term, right? If you have an initial term of the sequence, a final term of the sequence, okay. A sequence with an infinite domain, right? So you start at one integer and then keep going up by one forever for the domain. It's called an infinite sequence. In an infinite sequence, the indices go to infinity in the positive direction only. Right? So you start at m, go to m plus 1, input m plus 2, input m plus 3, and so on. All right, a sequence can be defined or specified by an explicit formula showing how the value of the term ak depends on k. For example, if I have d sub k equals 2 to the k for k greater than or equal to 1, the infinite sequence d sub k starts with 2, 4, 8, 16. Right? I plug in 1 first. See, it says k starts at 1. K is greater than or equal to 1. So I plug in, d1 would be 2, d2 would be 2 squared or 4, D3 would be 2 to the cubed, which would be 2 cubed would be 8. D4 would be 2 to the 4th or 16. That's the first 4 terms they got there. And then they got an ellipsis. Now again, this particular formula here, in between the two blue segments, that's called an explicit formula. It just tells me if I want the 100th term, how to find it. Just plug in 100. And notice that the definition doesn't depend on any previous terms. If I want the 100th term, I just need to plug in 100. I don't need to know what the 99th term was or the 98th term. All right. So it's called an explicit formula. All right. So here's an example. I'll let you play this on your own. This is pretty simple stuff, I feel. All right. So participation activity. Define the sequence AK here, beginning with A sub 1. So A1 is 7. That's the initial term, 7. What's A2? Well, if that's A1, then that's A2. Right? It's 10. Very, very easy. And what is the index, right, the subscript of the term 16? Well, that was A1, this is A2, this is A3, so the 16 is A4. So it's got an index of 4, a subscript of 4. What is the final index? Not the final term, the final index. So A1, A2, A3, A4, A5, A6. A7, the final index is 7. The final term is 25, but the final index is 7. And consider the sequence defined by the formula bk equals k squared. Again, an explicit formula telling you exactly what a particular term is by just plugging in a number, plugging in the index. Starting at 2, see k is greater or equal to 2. What is the third term of this sequence? Now be careful. They said third term. That doesn't mean plug in 3. All right, let me show you. So we're given this sequence. Right? The formula for it is this bk equals k squared, k greater than or equal to 2. So the first term, right? A term is an output. A term is an output. So the first term is when k equals 2, right? Where they're telling us to start. So that would be, 2 squared, that would be 4. And then the second term, the second output, would be when k equals 3, or you get, b sub 3. b3 would be 3 squared, or 9. And then the third term that they're asking for, the third output in the sequence, the third consecutive output, the third term in the sequence is when k equals 4, right? So not when k equals 3. Third term is the third output, the third term in the sequence when you write it out consecutively. And that would be k equals 4. 4 squared is 16. There's what they're asking for, right? The third term, the third output. So 16. Right? So be careful, with the numbers there. Know what index the sequence is starting at, so then you can figure out the first term, second term, third term, fourth term, the consecutive outputs in order. All right. So now we're going to talk about increasing and decreasing sequences. All right. So a sequence is increasing if for every 2 consecutive indices, and it's just the plural of index, every 2 consecutive inputs, k and k plus 1 in the domain, the outputs, the terms, a sub k is less than a sub k plus 1. So basically every term is bigger than the term before it. Sequence is increasing. A sequence is non-decreasing if for every 2 consecutive indices k and k plus 1 in the domain, ak is less than or equal to ak plus 1. So that means every term is bigger than the one before it or the same, but not less. Right, that's a non-decreasing. It's always going up somehow or staying level. So notice that an increasing sequence is always non-decreasing, because the greater than part or the less than part is always satisfied. So for example, 2, 4, 5, 6, that's bigger, 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 increasing, and also not decreasing, right? But here's 2, 4, 4, 6. You're getting bigger, staying the same, getting bigger, staying. It's either getting bigger or staying the same. That's non-decreasing, but it's not an increasing sequence because it's not always getting bigger. Right? And the same thing goes for decreasing and non-increasing. Right? Decreasing is always getting smaller, and non-increasing is either getting smaller or staying equal all the time. Right? So you can be both decreasing and non-increasing. Every decreasing sequence is not increasing, but not every non-increasing sequence is decreasing. Right? Okay. So quick examples here. Getting bigger, stays the same. So this is non-decreasing. Right. But it's not increasing though, because this last part, 3 goes to 3, that doesn't get bigger. Right? An increasing sequence is always getting larger. 4, 3.5, 2, -1. This is always getting smaller, so it's decreasing. And remember, every decreasing sequence is also non-increasing. Now this is both. Always. This is what they call a constant sequence. It's always the same value. So neither non-increasing nor non-decreasing. Yeah, this is non-increasing and non-decreasing. This is both. Right. It's just staying the same all the time. It satisfies both definitions. All right. So now we're going to get into some special examples, special types of infinite sequences that you may have seen in a previous algebra class before or pre-calc. I don't know, whatever you've taken. But yeah, if you haven't seen them before, here they are. So one of them is called a geometric sequence. All right, so a geometric sequence is a sequence of real numbers where each term after the initial term is found by taking the previous term and multiplying by a fixed number. This fixed number is called the common ratio for that sequence. Now a geometric sequence can be finite or infinite. So basically what this is saying is that every term is the previous term multiplied by some number, the same number every single time. So their example here, 4, then 2, then 1, then a half. You see this 4 times a half is 2. 2 times a half is 1. 1 times a half is a half. The next term would be a half times a half, which is a quarter, and then an eighth, then a 16th, then 1/32nd, then 1/64th, and so on. And that number that you keep multiplying by to get from one term to the next is called the common ratio. Okay. Let's see. Let's give you some other examples. So here's an infinite geometric sequence. Here's a finite geometric sequence, right, with only so many terms, with common ratio -1. Yeah. And then here's a little formula. If the initial index of an infinite geometric sequence is 0, so they start off with plugging in 0 for k, s sub k, then the explicit formula defining the sequence is this. Sk is equal to a times r to the k power. For again, you're starting at 0, k greater than or equal to 0. Here, the a is the initial term, and r is the common ratio, the number you're multiplying by. And they give an example here with interest rates and all that. You can read that on your own. All right. So for example, let s sub n be a geometric sequence that starts with an initial index of 0. The initial term is 2 and the comma ratio is 5. What is s sub 2? All right, so again, I'll go to some paper. All right, so we're told that we have this sequence s sub n. We're told it has a common ratio, which is that lowercase r, common ratio of 5. And they also told us the initial term, which in that little formula was given by a just lowercase a, is 2. Now, remember they're doing n. They said they're going to start the index off at 0. Right, so I'm having n be greater than or equal to 0 here. So the first term, which is s sub 0, the first output, again, is the initial term, 2. The second term, which will be s1, is again how do you form the next term of a geometric sequence? Is you take the previous term, which is 2, and multiply it by the common ratio, right? And notice that this is just a times r to the first, right? Now this is 10, right? 10. And then the second term, the third term, the third output, which is s sub 2 here, because we're starting at 0. It's again the previous term, which is 2 times 5, or 10, but then times 5 again, right? That's how you form these next terms in a geometric sequence. You take the previous term, keep multiplying by this common ratio. Well, that would be 2 times 5 squared, which, if I use the letters here, you see is a times r squared. And like they were saying, in general, for s sub k, if I want to go down to the k plus first term, s sub k would be whatever a is times whatever r is to the kth power. Now again, that's if you're starting with an initial index of 0. So 2 times 5 to the k. Right? And don't forget order of operations, right? You're doing the 5 to the k first. You do exponents first, then times 2. Don't do 2 times 5 and make that 10 and then raise to the k power. Remember your order of operations. Now, this is 50, right? And that's what they wanted, right? They wanted what s sub 2 was. They wanted that third term in the sequence, 50. So here again, let s sub n be a geometric sequence that starts with initial index of 0. So again, the first term is when I plug in n equals 0. The initial term is 16. Common ratio is a half. What is s3? So again, back on some paper here. So the initial term, again, is a is 16. We're looking at a geometric sequence called s sub n starting at 0. Common ratio is a half. And again, if your initial index is starting at 0 and it's a geometric sequence, the formula for the nth term or the kth term, whatever term, is just the initial term times the common ratio to that power. So, again, s sub 0 is easy enough, right? Again, that's 16. Now I could go through and find s1, s2, s3, but they want s3, right? And we know a formula. S3 would be the initial term, 16, times the common ratio to the third power. So this is 16 times, 1/8, and 1/8 of 16 is simply 2. Again, you could have done this by saying S0, 16, then times a half, 8. Then S2 is times a half, 4, and then times a half, you get 2. But the reason I want to use a formula, an explicit formula, is because what if they asked for S100? What if they asked for S100? I wouldn't want to do this 100 times. I would just plug in 100 for my power. All right. Okay. So back here, that's 2. All right, and here, consider the geometric sequence 3, 6, 12. Now they tell you it's geometric. And they ask, what is the common ratio? The common ratio is just that r, that number that you multiply by every time to get from one term to the next. Or just divide consecutive terms. Take the second term divided by the first term. 6 divided by 3 is 2. 12 divided by 6 is 2. The common ratio is 2, right? I'd have to keep multiplying by 2 every time. So hopefully that's easy enough. Now for a geometric sequence, you kept multiplying by the same number every time. For these arithmetic, now I know it looks like the word arithmetic, and it is the same spelling, but in this context, in the context of a sequence, it's pronounced arithmetic. So in an arithmetic sequence, you're adding the same number every time, right? And that number that you keep adding, that fixed number, is called the common difference. So they give an example here, so say this sequence starts at -1, then you got 1.5, then 4, then 6.5. That common difference, which will be labeled by a lowercase d, is 2.5. Just keep adding 2.5 every single time and get the next term in the sequence. Right, and the initial term is called A0. So again, we're going to start a lot of these with an index of 0 and then work from there. And here's your explicit formula. If the initial index of an arithmetic sequence called t sub n is 0, then the explicit formula defining the sequence is t sub n equals the initial term t sub 0, the first term, plus d times n, where again d is that common difference, right? Common difference d, and that's the number you just keep adding every time to get the next term. So notice from these formulas, that the geometric sequences, right? Geometric sequences are basically exponential functions of the index, right? The indices, the inputs are in the exponent. These arithmetic sequences are linear functions of the index, right? So they'll grow much more slowly. You can read that example. All right. So here, let S sub n be an arithmetic sequence that starts with initial index of 0, right? The initial term is 3 and the common difference is -2. What is S sub 2? So again, I'll write this out. Grab some paper here, and so we're given this sequence again called S sub n. They told us it's starting at 0, right? So n being an integer greater than or equal to 0. They told us the initial term, right, S sub 0, is 3. And that common difference, the number that you just keep adding to get from one term to the next, that is represented by lowercase d for difference, said that was -2. So here's So how you get the next term. The second term, S1, would be the previous term, 3, plus this common difference, plus -2. So if I write this in terms of the initial term and the common difference, this is just S sub 0 plus 1 times -2, or 1 times d, sorry, plus 1d. Now 3 plus -2 is 1. So the second term, S1, is 1. Then S2, right, would be the previous term, which is 3 plus -2, and then just add -2 again. You just keep adding that common difference. Well, that's just 3 plus, and then when you add something multiple times, you get a multiple of that number. This is 2 times -2. So what I have here is the initial term, 3, plus 2 times the common difference, plus 2d. And this is just 1 minus 2. 1 plus -2 is -1. So, and this is what they wanted. But you see, if I went in general here, the nth index, the n, that would be the n plus first term, would be the initial term plus n times whatever n times d is. And that's what we were seeing there with S1, S2. It was S0 plus 2d. S3 would be S0 plus 3d, and so on. But all they wanted was this S sub 2, this third term in the sequence. 3, 1, and then, -1 is what they wanted. And then here's an arithmetic. They're telling you it's an arithmetic sequence. 7, 4, 1. What's the next term in the sequence? Well, what's being added every time? Well, 7 to 4, that's -3. And then 4 to 1, that's adding -3. So the common difference here, the d, is -3. So subtract 3 again. 1 minus 3 is -2. The next term in the sequence is -2. Very, very simple. All right. Then the challenge activity. There are 6 of these. I'll just do a couple. It says enter the next 3 numbers in the sequence of even numbers. So come on. Now the sequence of even numbers would be an example of an arithmetic sequence, right? Because you're going to be adding 2 every time. And then you go 2, 4, 6, 8, 10, 12, and 14, 16, 18, and so on. Let's see what the second level looks like. Same thing. Now I see increases by 5. So another arithmetic sequence. You're adding 5 every time. See the third level. See, it's they're telling you it's geometric. Right, the first 3 terms. Initial term 2, common ratio 3. You keep multiplying by 3. Another geometric sequence. An arithmetic sequence. Common difference is the number you keep adding every time. And finally, another arithmetic sequence. All right, then you have additional exercises. Now, some of these are a little more complicated than the ones I looked at. But just here you're asked to give the first 10 terms of this first is the ceiling of the square root of n, and you start with an index of 1, right? So the first term here, when you plug in 1 for n, would be 1, right? The square root of 1 is 1. The ceiling of 1 would be 1. And when you plug in 2, square root of 2 is 1.4 something, but then the ceiling would be 2. And so hopefully you understand what these expressions mean. Now they do say when you have a log, pay attention, logs are to base 2. Logs are base 2, not 10. So unfortunately, if you use the calculator and you put in the log button on the calculator, that's going to be wrong. This is log. They're saying logs are base 2, not 10. So be aware of that, please, and pay attention to your ceilings and floors and all that. Then after that, you indicate whether the sequence is increasing, decreasing, non-increasing, or non-decreasing. It may have more than one of those properties. Remember, if it's increasing, it's also not non-decreasing, and if it's decreasing, it's also non-increasing. And if it's the same value all the time, it's both non-increasing and non-decreasing. So it could have more. It could have more than one of those properties. And then you got more stuff, more stuff, more stuff. I don't think maybe I did assign all these, but these should be on your assignment 8. Some of these exercises, if not all of them. And if they're not all on there, I would still recommend doing all of them, right, just to get more familiar with the material and more practice, get better at it. And of course, you got the solutions you can look at, check your work. Please, though, try to work out the problem, try to figure things out before you look at the solutions, because if you're just copying solutions down, you're not going to learn anything. And of course, if you have any questions, send them my way, let me know. And thank you very much for watching.